So we begin today's discussion by asking, what is the kinetic energy of this object rotating around an axis? It's just got some random shape, it's got some mass. I don't know how that mass is distributed, but I've got that object and it's rotating. And I want to figure out what kind of energy it has. Well, we're going to start by kind of breaking this down into littler bits. So let's imagine that I'm going to take, I'm going to kind of carve up my object into little bits. So I carve up a little bit here, which we'll call M1. And this is going to move with some velocity V1. And I could take another little bit over here, which we'll call M2. And it's going with some velocity V2. And I could pick a third bit over here. We'll call this M3, R3, V3. You get the idea. I can kind of cut this up into tiny little chunks. And the idea is, if I then add all those chunks back together, well, I could do 1/2 M1V1 squared plus 1/2 M2V2 squared plus 1/2 M3V3 squared, and so on and so forth. But we're doing everything in rotation. We don't really want V's laying around. So we're going to apply our favorite little tool here, V equals R omega. We're going to take everything into rotation land here. So we're going to rewrite this kinetic energy this way. 1/2 M1, let's see, V squared would be R squared omega squared. So I'll have R1 squared omega squared plus 1/2 M2 R2 squared omega squared plus 1/2 M3 R3 squared omega squared, and so on and so forth. Notice, by the way, that I'm using the same omega. It's not omega 1 or omega 2. I've got the same omega everywhere because, of course, we know that on a rotating object, every part of that rotating object is the same omega. Now, a funny thing happens. I can kind of rewrite this. If I grab all of those MR squareds, M1 R1 squared plus M2 R2 squared plus M3 R3 squared, and I kind of factor all those out, I get something that looks like this. 1/2 something times omega squared. And this is very tempting because this looks kind of like our normal kinetic energy, 1/2 something something squared. So what we're going to do is we're actually going to take this middle bit and we're going to give this a new name. We're going to call this, we're going to give this a new name. So this is going to be 1/2. So the sum of mi ri squared, to get a little mathier, times omega squared. And we're going to take this this little quantity here, and we're going to say we're going to give this a new name, and this name happens to be the rotational inertia. It also goes by the name moment of inertia. You'll see those interchangeably. And it is defined as the sum of all the MR squareds for an object. So however many parts an object has, I'm going to add up all of the MR squareds for it. I want to note a couple things here. First of all, that does a really nice thing to our kinetic energy. It turns it into 1/2 I omega squared. And this is, again, really satisfying because we expect quite often, it should look like 1/2 mv squared. Well, 1/2 I omega squared. So I is, in fact, our rotational version of mass. So instead of mass, we consider our rotational inertia. It has units of kilograms times meters squared, at least in normal SI units. And what does it tell you? Well, it tells you how easy something is to turn. So a larger eye is harder to turn, harder to spin. And what's unusual about this is that it depends on our choice of axis. And just to elucidate this in two ways. One, if we look at our original object, I know I drew an axis kind of right in the middle. If you imagine that we instead put an axis here, well, that's going to change all of the radii to all of the different parts of my object. And if the radii change, my eye is going to change. So it depends on the axis. The same shape can have a different eye depending on where the axis is. And you may have experienced this in real life if you've ever played, say, baseball. One thing they often tell to new batters or younger batters to control the bat better is to choke up a little bit to shorten your grip on the bat. That changes the axis of rotation, makes it easier to spin. So let's do a little test here. I'm going to draw a little figure here. So let's imagine that we have a 2 kilogram mass connected to a 1/2 kilogram mass. We're going to assume that what's connecting them has no mass or negligible mass. And we're going to put the axis right here. That is, we've got 0.1 meters this way and 0.4 meters this way. And we want to calculate the eye of this object. Well, we can add up all of our MR squareds. In this case, we only have two objects. We have a 2 kilogram mass, and its radius is 0.1 meters away from the axis. All of these radii are always measured to the axis, plus 0.5 kilograms times 0.4 meters squared. In this case, this will give us 0.02, and this will give us 0.08. And I just want to point out real quick that even though the 0.5 kilogram mass is smaller, because it's further away, it makes a larger contribution to our moment of inertia. And I know that 0.02 plus 0.08 is 0.1 kilogram meters squared. So that is the rotational inertia of this object. And you could convince yourself, by the way, and I will have you do the calculation right now to see if you can do it. I'd like you to convince yourself, by the way, that if you put the axis through the end, or sorry, it really should be right in the middle. If you put the axis right in the middle of the 2 kilogram object, your eye would be a little different. Your eye would in fact be, and I'm going to let you find it right now. You should have gotten 0.125, a little bit higher. There is one other case, though, that we need to consider, which gets a little bit strange, which is, and we're going to get to that in the second part of this video, which is, what if my object isn't a point mass? What if instead I have a continuous object, like a stick or a ruler or a rod, that I can't break up into individual discrete little bits? How do I find the moment of inertia of an object like that? So we continue our discussion of kind of moment of inertia with objects that are continuous. So rather than being made up of a couple different point masses, they are continuous objects. So we're going to take the example here of a rod or stick of total length L and total mass M. And we are going to rotate it through an axis right in the middle. One of the first things we're going to want to do is establish a coordinate system. We always want to do that in physics. So I'm just going to declare wherever my axis is to be x over 0, or x equals 0. I think that's usually the easiest thing. So how do I even start here? Where do I even begin? So the first thing that I want to do is kind of like we did before. I'm going to take a little slice of my object. I'm going to take a little slice out of my object. This slice, by the way, will be some distance x, some position x. And I'm going to say that the slice has a thickness or a width of dx. And so what I could do is I could say, well, this little slice in here has some mass and is some distance away. And so it's going to provide a tiny little bit of my moment of inertia. It's going to provide a tiny little bit of my moment of inertia there. Well, how much is it going to be? It's going to be mr squared. Mr squared. Now, sometimes you'll see this written this way as r squared dm, which is a little bit of mass. And in fact, you'll see this written, the total I written as an integral r squared dm. And that's how it appears on your equation sheet. So let's take a look at this little slice and ask how much mass is in there. What is the mass in my little slice? Well, my thing has a total mass m and a total length l. So what that means is that for any little unit length, I actually have a density, a linear density, equal to m over L, kind of kilograms per meter. So you may not have worked with density all that much before, but one of the things that I can do is if I want to know how much mass is in that little section, I can just take my linear density and multiply it by dx. So I get m over L times dx in that little slice. If you like, you can think of this as kind of the mass of the object times what fraction of the length we've cut off. In this case, this actually allows me to set up my integral here to find the I, because I'm adding up all of these little slices. So each slice has a mass of m over L dx. And how far away from the axis is, what's its radius? Because we're still effectively adding up all of our mr squareds. What's my radius? Well, I'm a distance x away from my axis, from my point of rotation. Now all I have to do is set the boundaries on this. Notice by setting the middle to 0 and having a total length L, this goes from negative L over 2 to positive L over 2. And this allows me to solve it. Well, x squared, I know how to do that. That's 1/3 x cubed, evaluated from negative L over 2 to L over 2. So this is going to give me L cubed over 8 minus negative L cubed over 8. So that'll actually be a plus. L cubed plus L cubed is 2L cubed over 8 makes L cubed over 4. One of my L's cancels out, and what I end up with is 1/12 ml squared. And this is the I, this is the moment of inertia for a stick around its center. And this is just one example. We'll see lots of different I's over the course of the year, and we'll do a couple more of them in class. We'll prove a couple more of them in class.